Okay, thank you, Mikhail. Hi, everyone. My name is Pedro. I am a PhD student. I'm doing a cocktail between France and Brazil at INSA and at Unicamp. Right now, I'm in Brazil. So, hello. Um, yes, as Mikhail said, this is a presentation about my master thesis work, and also with a focus on the actual challenges of using MLIR for what I was trying to do, which is Dataflow compiler. So this presentation has two parts. The first part is an overview of my compiler itself. I'm going to go over the basics of Dataflow. I'm going to talk about my compiler and show you guys some results. And in the second part, I'm going to focus on the MLIR dialect that I created for the compiler. What I needed it to be able to represent and the difficulties I had with having MLIR represent these abstractions, the solutions I arrived at, and then if we have time, we can open for some discussion. So starting with my compiler. Dataflow, I'm not sure if everyone here is uh, uh, knows very well what it is, because it is many things. It is a very mature research subject. It was created in the 60s, and it has been a successful approach for many different kinds of applications. It's been used in real-time systems, in reactive systems, heterogeneous networks, high-level synthesis, etc. And because it's been used in many different applications, it also has many different models of computation associated with it, with slight differences that make it really mostly useful with specific applications in mind. So because of that, and because each different team that adopts a data flow model of computation for its work has a slightly different goal in mind. There isn't much focus in intercompatibility between tools, even though there's more in common than difference between the different data flow models of computation. And so my main goal with my project was enabling different areas in Dataflow be able to access the state-of-the-art in compilers more easily and facilitate the collaboration between different projects. At the same time, I wanted to make the advantages of Dataflow modules of computation more accessible to the overall compilation community, because these two areas of research have mostly diverged with the years. And so I wanted to be able to reuse components such as implementations of actors and schedulers and optimizations and runtimes. And for that, we chose to use MLIR because, as we've seen, and as it has been very thoroughly shown in the talk so far, MLIR this is where MLIR really shines in intercompatibility and reuse of abstractions. And so that brings us to our main problem, which is what are the requirements for a common data flow format that is useful while within MLIR's constraints. Just covering a little bit of data flow. In general, all data flow models of computation model an algorithm as a directed graph, where the vertices or the actors are computation units that act on act on tokens of data. Tokens have a fixed size, and actors consume tokens from its input edges and produce them into their output edges. And edges are first in, first out data structures. When you create your algorithm like this, it automatically it makes explicit the data dependencies between the different parts of your algorithm, and also makes it very easy to create a parallel schedule, because parallel paths inside of a graph can be executed in parallel without any conflict. And depending on the model of computation, we can do some of these analyses even at compile time. Going on. It's important to say that Dataflow graph is not just DAG, right? A directed acyclic graph, because Dataflow graphs allow for cycles and for delays. Delays being starting data inside of an edge that allow for these cycles to exist without reaching a deadlock or a starvation. As I said before, there are many different modes of computation in the family of Dataflow with different levels of strictness, where usually the most strict level, the less flexible you are when developing your algorithm, but the more guarantees you have at compile time. So you can create a very optimized schedules at compile time. The more flexibility you add to the model of computation, the more flexible it becomes for programming, but the more difficult it becomes to schedule. And the more unconstrained the model, the more expressive and easier to use it is. Starting from more restrictive to less restrictive, we can start with synchronous Dataflow, or SDF, where each time an actor executes, it always consumes the same amount of tokens from its inputs and always produces the same amount of tokens in its outputs. Within these constraints, the schedule can always be generated statically with no runtime cost. So we know that no matter what the data is, we can always execute these actors in the same order and in the same course. One of the advantage of static Dataflow is that we can detect inadmissible graphs at compile time. For instance, if we have a graph that leads to an imbalance in the amount of tokens that an actor consumes or produces, this can be detected before we run the algorithm. Cycle static Dataflow is an expansion of static Dataflow, where the data rates are not always the same, but they are cyclic and predictable. It still doesn't depend on the runtime data, and it has the property that this can be transformed into a static Dataflow graph if necessary. The advantage is that this, if your algorithm can be represented like this, it consumes much less space. Going on with the with the flexibility, we can add a parameterization and interfaces to our model of computation, which means being able, when we talk about parameterization, we can add parameters which are data that can change the behavior of an actor, but that is not part of the actual tokens that it consumes or produces. So for instance, this is useful if you want to create an algorithm that can operate on different image sizes, for instance. The size of the image is the parameter for the algorithm. And interfaces allow for an actor to reference a subgraph. So we can have some hierarchy in the definition of our graph, and to allow for some modularity and code reuse. And finally, we arrive to the dynamic models of computation, where the behavior of an actor depends on the actual data that's contained inside of the tokens. So the amount of tokens that it produces in its output parts can depend on the data that it consumes in its input parts. This turns out to be Turing complete, so this cannot be totally predicted at compile time, and so we need some kind of runtime to deal with allocation and deallocation of memory as needed. So this has a runtime cost. Just clearing up some terminology, because, as I said before, there are many different areas within Dataflow. Sometimes it happens that different areas have different terminologies for things. So I added this slide here to clear things up. The word actor is sometimes ambiguously used to refer to a node inside the graph, or to the implementation of this node. And since we're talking about the low-level implementation, I like to draw these distinctions between them, and and show that two different nodes can have the same kernel implementation. In this case, the kernel is a function. The nodes are the different instances of this function.
Pedro?
Pedro?
Yes?
Yeah, maybe one thing that is missing in some models is the explicit notion of a delay node. So, I mean, you can represent delay as a specific kernel implementation of a node, but in some models, it's important to know that the node is actually a delay or has a delay inside. How do you represent that?
Oh yeah, delays. I was going to cover that in a bit, but I usually treat delays as a property of an edge, and not of a kernel.
That can be a problem, I think, but okay, let's see.
Yes. Yeah. Let's discuss that after. Well, going on. Some related works to my work is Prism, which I'm sure everyone is familiar with.
No. No.
Not really? No. Well, it was developed at INSA, which is my. Are you guys at INSA right now? just so you know.
Yeah, we are INSA, but many people are not from INSA.
Okay. Just clearing this up. Prism is a Dataflow IDE based on Eclipse, and it generates C code as a target, and it has a multi-core scheduler, and we design our algorithms with a graphical interface. A lot of work has been put in it. Has lots of state-of-the-art optimizations, and the graphs are stored in declarative XML format. And another project that I use is diff, Dataflow interchange format. It is part of a Java-based library, and it's a simple human-readable grammar for defining Dataflow graphs. So it consists of a topology with nodes, edges, interfaces, parameters, all of those abstractions that I mentioned before. Importantly, it makes no assumptions about the model of computation. So in theory, it can be used for any applications. Well, moving on. This is my compiler. I read diff as my input for the topology of the Dataflow graph. I parse it into my own MLIR dialect. I schedule and bufferize this dialect directly and generate some LVMIR. And this LVMIR is linked against separately compiled kernels into a final binary. So far, there is nothing new here. I'm just using MLIR as a normal straight-of-the-mill compiler framework. But then the novelty is that I also allow reading the kernels in C code using polygeist as MLIR frontend for C. And then once we have both the kernel and the topology code at the same place inside of my compiler, I can do some co-optimization. I can use information from the topology to alter the kernel implementation for my benefit. So in this case, I do that code elimination pass that allows us to remove code that is unused, where this information would not be available for a normal C compiler. As an example, here we have a Cartesian to polar function where we read an x and y coordinate and output a radius and an angle. Assuming that we are only interested in the radius of this function, we can automatically detect which operations inside of this function are only related to the outputs of data, and you can remove them automatically. So this is the original C code, and this is the respective MLIR code as generated by polygeist. I've highlighted the operations that are only related to the second argument with the OR argument, and the ones that are only related to the theta argument. Here, if you want to get rid of the theta argument, we can get rid of this function call for trigonometric function call, which is very expensive. And we can also get rid of the space that would be necessary to store this output. So we save both cycles and memory. For results, we've compared against existing SDF applications available in the Prism project. We compared the performance with the single core scheduler for Prism. I did not implement a multi-core scheduler because of the that was not really the focus of my work. I was more interested in the proof of concept of the compiler transformations. And we got comparable results, except for very large graphs. In this example in this artificial example that we created, where we read a video in RGB format, and we want to convert it into grayscale using an actor that converts from RGB to hue, saturation, lightness, and we discard the hue and saturation values. Here, just by using our DC, just without using our DC path, only using my scheduler, we save about half of the memory. And using RDC, we save 2/3 of the memory, which is to be expected, because we're removing 2/3 of the buffers that would be required for this execution. Prism by itself does not support unused outputs. So in the implementation that I created for Prism, it just writes the unused data into a global buffer. Just because of the smaller memory footprint, we got a speed up, and because of the saved cycles, we get a lot of speed up also. Another applications that we tested against is a simple Sobel filter. Here we didn't get any speed up, probably because this application is very simple. There is not much flexibility in where to in how to schedule this application. And we tried with a very large graph, in this case the scale invariant feature transform, which is image processing algorithm. This has dozens of actors, hundreds of edges, and thousands of lines of code. In this case, we do much worse, probably because I don't have as many of the sophisticated optimizations that Prism has. Well, that's basically it. We did get the dead code elimination pass published at CIPS last year, which was nice. But there is still a lot of work to be done in my compiler, which is what I'm working on in my PhD. About the MLIR dialect, we had a list of requirements of things we needed to represent in our abstraction. Namely, we needed a list of actor interfaces, which are basically function signatures, with a name, a list of parameters, input and output ports. And each part needs to have a name, a type, and information about the token rate. So it's not exactly the same as a function call. And so I needed to create an operation specifically for that. We also needed a list of nodes because, as we said before, more than one node can use the same actor. So it's basically just a reference to an actor that respects the same signature. And so we needed to implement type checking and rate consistency, checking for the consistency in rates. And a reference to the implementation, which could be a C function, link time symbol, or a subgraph for the case of interface Dataflow. And then we need also a list of edges between the ports. And edges may have extra data, such as delays, as I mentioned before. I treat delays as a property of the edges. And they need type checking to ensure that the producing and consuming ports match. I was also thinking about extensibility for different modules computations. Even though I only implemented synchronous data flow, the idea is that this could be reused for other modules computation. And create and respect the separation between graph and kernel. Unfortunately, this is not very MLIR-like, by which I mean it doesn't use, as I say, a single static assignment to encode the graph. I'm not using the outputs of operations as edges. I'm using edges as their own operations, and I'll show you why in a second. My first approach was to have two dialects, one higher level dialect that has a high level topology where everything is referred to by name. That would be easier to generate directly from the ESC of the input languages, such as the Prism XML and the diff. And the idea is that it should remain human readable and editable by hand. So trying to avoid a name angling and indexing parameters. So we want to be able to refer to edges and parameters by name still, and keep the interface recognizable for debug purposes. And another dialect that respects the SSA philosophy that MLIR encourages. So using MLIR's graph traversal and enabling the built-in type checking and pattern matching framework that MLIR has. The declarative dialect is the first thing I implemented. It is, as I described before, I have a list of kernels, which contain a list of parameters and parameters, inputs and outputs. The parameters are a names and types. The types can be inferred from the context, either the graph or a higher level graph. In MLIR, differently from LLVM-IR, we are able to have hierarchical blocks. So if we have an infer parameter, we can look for this value higher up in the hierarchy. And inputs and outputs consists of a name, a type, and a rate. We have nodes, and the nodes consist of just a name and a reference to their implementation, which can be a kernel or can be another graph. And we have edges, which are two pairs, two name port pairs. In the case of cyclic graphs, we can have delays as part of the edge. And then I started working on a middle level, more MLIR-like dialect, where the graph is represented by the SSA format of MLIR. Unfortunately, I ended up deciding against it because of a number of reasons. First, we lose the ability to have names for the output ports. Even though we can give names to the values in MLIR, it's not guaranteed that these names are going to be maintained between different passes. These are really thought of as temporary values in the MLIR representation. And so if I use this representation, the names of the parts and the types are lost, and we only get the connections directly.
Sorry, can you hear me?
Yes.
Yeah, if you only care about debug info, you can do it. I mean, you can attach, just like an LLVM, you can attach metadata to preserve variable names. And if you capture port names in that way, it should work. But there may be other reasons you want to preserve port names, but I don't see it actually.
Yeah, we would also, if we wanted to use type the MLIR's type checking infrastructure, we would also have to encode the types and rates of the parameters inside of the type of this value. And so if we have an output port that, for instance, outputs 2 chars, and an input port that receives 1 char, they would have different types, and you would have to determine that they're compatible inside of the MLIR type system. That
Which you can implement that in a like custom type system with a bunch of custom C++ in the dialect, but I'm not saying it's easy, but it's
yeah, exactly. I thought it wouldn't be worth it. And the second reason is that we would lose source information, because in the original source code, the edges are represented as their own lines of code, right? And in this case, we can't assign a source location to a specific value, only for the whole operation. And so that's another reason I avoided it. And in the end, if I wanted to add delays, as I'm treating delays as part of as a property of the edge, I would have to create another operation just for the delays, which would be the same thing that I was already doing, right?
So yeah, that could be considered a feature. So if you don't model synchronous data flow, but data flow synchronous languages, sorry for the stupid names, like Lust, delays are explicit. If you model circuits, like sequential circuits, they will also be explicit. What's the problem with delays as operations?
It's not a problem. It's just that when you're adding a delay, it's another step for type checking, right? Because the delay needs to ensure that the types going in is the same as the type going out.
But assuming you have solved that problem in the first place, which is not easy, I think it's too much of a burden. But, I mean, we began that conversation a few months back at the ODM meeting where you presented it, and so I see that you have more reasons to do what you did, but I'm still not convinced this is the way to go.
Yeah. Well, in the end, what I ended up working directly. Sorry. I ended up working directly with the declarative IR. Not only because of all of those reasons, but also because I didn't have much time. So I decided to focus on the back end, and I just implemented all of the type checking manually. was actually more convenient because I needed to go through the whole graph anyways for the consistency checks for the SDF. So it ended up working out, but I'm not particularly happy with the way it turned out in the terms of extensibility. I think if I wanted to go back and make it be more useful for other modes of computation, I would have to do something like this.
Valuable. I don't know how much time you have left. Like, negative, I guess.
No, yeah. This is the last slide.
This is part of your business, then I would strongly encourage you to try that.
Yeah, and like it's exactly as you said. Like this is not ideal for Dataflow models that don't have kernel and graph separation. Like as you said, it's like explicit. When you have Dataflow information encoded directly inside of the actor. And then well, that's basically it. I was curious about what you said about having delays as part of the actor and not the edge.
So was it a question?
Yeah, I guess it was a question. Let's just thank our speaker and we get to the question.
Thank you.
So I'll try to rephrase Pedro's question. I think he was interested in the idea of modeling delay as part of an actor.
Yeah, I think it's mostly a matter of making it explicit that an op is a delay or an op has a delaying effect. Like there are more modular ways of compiling synchronous languages, for example, where you just mark delaying input-output relationships in nodes. So you need to know which input will, which output will be sensitive to an input with a delay guarantee. So that breaks cycles basically in you compile for causality analysis, etc. That's important. So that could be captured in the op as just attributes marking which inputs and outputs are involved delays. You can do even simpler things, but more modular ways of compiling synchronous languages do that. I don't think it may not be very useful for like plain CSDF, SDF signaling and stuff like that, but I don't think it causes any additional problem either. It's just more verbose. But in general, everything should be a value or an op. If it's not, probably you're wrong. And if you really cannot do it with value or an op or type, that means maybe MLIR has to change. But because if you cannot model data flow, whatever flavor of data flow with MLIR, it's very frustrating. I mean, it should be possible.
Yeah, I agree. There are a couple. I actually, I think you specifically were there, but I've given this talk in the MLIR open meeting, and I've actually removed this part from these slides, but I had a section where I had some suggestions on expansions for MLIR that would make my life easier.
Oh yes.
And I think a lot of other people also, because things like being able to address parameters by name instead of by position.
Yeah, I remember that. Yeah, that would be interesting, and also more type systems. Better support for custom type systems and superposition of multiple type systems, as I was saying earlier. So you may face a lot of opposition when coming up with such suggestions, but if you come with an implementation and you work with experts to try to make it smooth, like transparent to people who have something running, maybe it's possible. I think this is worth it, but that may go beyond the scope of the PhD.
there
It's fixed. There are ways to still make some changes.
yeah. Their suggestion was to start with writing this functionality as a wrapper. So by using just the functionality that already exists, like attributes and everything else, and just extend the existing operations and everything. Should be possible to add this functionality without breaking everything else, I think, in the current MLIR. But at the same time, they are constantly adding more features, so who knows?
Any other question online or here?
Comment has just been said. You said that you never know what may come, but the good thing, I mean, I think one of the strengths of things like MLIR, LVM, and things like this is if you have the time, of course, and if your PhD supervisors are okay with it, of course, you can always try to upstream, contribute, or maybe steer a little bit of conversation towards what you're wanting to achieve. So try.
And sometimes someone else will pick it up, like the recent properties proposal of Mehdi that made it upstream. That if it had come from someone like nobody knows, it would be hopeless. But if you discuss it with more people who get support it, understand it's actually feasible, it can be made transparent, etc., then although it's a very it affects everything basically. Everything depends on properties eventually. But, it's a low-level implementation detail, etc. But if people trust that you can do it and the code is there, then why not? It's possible.
Yeah, that's what I was thinking when I said they add new features constantly. But well, we shall see. I would love to have time to work on a feature like this and upstream it, but I'm not sure if that's realistic. Any other questions?
Yeah, slightly disconnected question. So as you mentioned SDF and that class of static data flow graph. So lots of machine learning models are static and data flow. Do they make interesting SDFs? Maybe they're just trivial, or do people have any interest in the SDF community in looking at ML benchmarks, ML models, and vice versa? Vice versa, I know the answer, but.
Well, my understanding is that these ML models are largely a specific case of SDF, right? But they're also largely linear, right? They don't tend to have very complicated graphs.
Graph neural networks, and I would expect to have some balancing issues sometimes. So you can look into that. There are even dynamic conditions sometimes in gate routing layers, etc.
Well,
but I've not seen much interest from the ML space. But I think people interested in static memory allocation, etc. They may ignore what has been done in the SDF space.
We're partly, I would add to answer of Pedro, we somehow a little bit looking into that, coming from the SDS perspective in the team. One of the challenges that I see is that at the coarse grains that can be seen as a data flow model, where there is a convolution doing a lot of things. For example, an operation like a convolution doing a lot of things, producing a new layer and then the next operation. But if we want to go at the lower level, like tiling, this is not the kind of information where we have reuse between different operations of the same data, which is representable in Dataflow.
Or like sliding window.
Yes, sliding window would not be representable in SDF, and maybe a bit more of a challenge. Not saying it's impossible, but right now an actor is consuming a fixed amount of token on a strictly non-overlapping window.
Yeah, but you can always cycle back tokens and modeling tricks. And so let's say it
Yeah.
can be implemented that way, but
Yeah, we'll have to see if those modeling tricks would help, or if there are other representations which are more amenable, at least in the fine grain, to do this kind of operation. But yeah, MLIR also would be a good opportunity for that, I have to say, to be able to use all the backends and all the
connected to the front end.
connected to, and also to the front end, to reuse all the infrastructures which has been already done, which is an uphill battle if you want to compare to anything else.
Yeah.
Definitely. Any other question? So thanks again, Pedro, for the last presentation for today.
Thank you.